how are we ever to prove that there are universes other than our own, and that they are run on different lines? Other universes, by definition, are not part of our universe, and so cannot be contacted. So it could be that the multiverse idea might also lie beyond the realms of science. When thinking about our universe being life-friendly, one can't help wondering whether there might be other forms of life out there. And it's intelligent. How does that affect the status of us humans? What do we know about the human brain and consciousness? Or to put it another way, what can a brain know about itself? Chemical flows, electrical currents. Some liken it to this, an elaborate computer. But unlike this or any other computer that's been built so far, the brain is conscious. It's aware of itself. All that physical activity is accompanied by feelings and emotions. This was an early attempt to try to associate different parts of the brain with different mental experiences. This shows a person when they are meditating and when they are not meditating. But which is which? Which one shows the person meditating? We can't tell. Not from just looking at these scans. Not until the subject tells us that that is what they're doing. They're meditating. Okay, once they've done that, when we come across the same sort of brain pattern in someone else, say, it's a good bet that it will be accompanied by the same sort of mental experience again. But without a subject volunteering the information about the mental experience in the first place, we get nowhere. In fact, why are there conscious mental experiences at all? We don't even know which things are conscious. I'm conscious. I know that from direct experience. You? Well, you have a brain like mine and you talk about having mental experiences, so okay, I'll give you the benefit of the doubt. How about this? Well, not exactly this, but a proper chimpanzee. Are chimpanzees conscious? Are they aware of themselves? Well, yes. But what about this? A worm. Is a worm conscious? Could they feel pain? Well, there's one way to find out. Cut it in half and see what happens. Both halves are writhing about. So what does that mean? It now has two minds, whereas previously it only had one? Or does it not have a mind at all? And what about these? Bacteria. You shouldn't have thought so. The sun? Well, no, definitely not the sun. Humans, definitely yes. The sun, definitely no. But where was the dividing line? How could we ever find out? This is the problem of consciousness. How to understand the brain in relation to conscious mental experience. Are we dealing with two separate things, a brain and a mind, and somehow they're interacting with each other? That's one theory, but it's not very popular these days. Or is there just the one thing which we approach in two quite separate ways? Atoms, electricity, spatial orientation, and another more language where we talk about pain and love and happiness, the kind of you would never find in a physics equation, all right? And one needs both languages understanding of what's going on. Consciousness poses a big, big problem. See how we'll ever have a fully satisfactory answer to it, one that everyone agrees about. It's a close encounter of the first kind with what I call the boundaries of the knowable. You see, science has its limits. In fact, science will grind to a halt. Scientific discoveries. Not when we've discovered everything, complete knowledge, nothing more to know, but when we've discovered everything that is open to us to understand, which is not the same thing. Don't get me wrong, it's not going to happen soon. And the applications of science, they'll continue. There'll all be plenty of scope for new gadgets and things like that, and updates of computers and PlayStations, that sort of thing. Technology will continue, but not fundamental science, not the discovery of new laws of nature. Why do I say that? In the first place, we have to consider what we do our science with. But how do we come to have a brain in the first place? According to the theory of evolution, it's something that has been fashioned it helped our ancestors to find food, shelter, a mate. It helped them to predators. It was part of their survival kit. Capable of understanding everything about the world. That wasn't necessary for our ancestors to survive. A second reason why we might not be able to complete our understanding of the world has to do with practical considerations. I'm what's called a high-energy nuclear physicist. It means I'm interested in discovering the ultimate structure of matter, what everything is made of and what holds it together. To do this, we have to accelerate tiny subatomic particles to great energies, and then we smash them together to see what happens. The big international laboratory where I used to work is in fact just a small section of a great giant circular machine, 27 kilometers in circumference. That's Geneva Airport, to show you in comparison, give you an idea of the scale. As a general rule, each time we've built a machine, we've made discoveries that were quite unexpected. And this raises a question, crucial piece of evidence. There's no reason why the final clinching experiment has to fit in with what we humans happen to be able to afford or can physically build. And without that last crucial piece of experimental evidence, our theories about the world could remain forever incomplete. And then there's a third reason for suspecting that science will eventually fall short of providing us with a complete understanding of everything. The fact that we can perhaps already discern where some of those limits might be. Stubborn questions that have been around for a very long time. Questions to do with the nature of space and of time, of matter, of light, stuff like that. Perhaps because, for us, they are intrinsically unanswerable. They are at the boundaries of the knowable. How are we to understand consciousness is but the first of those questions. Stop sulking, Wally. Sorry if I frightened you. No animals were hurt in the making of this program. Okay, you've had your 15 seconds of fame. It's now time to go back to work in the garden. All day long we have to make choices. Okay, I happen to choose this one. I could just as easily have chosen a brown one or a red one. Or could I? Was I really free to choose? We do all our thinking with our brain, but the brain is a physical object. The behavior of physical objects is governed by the laws of nature. Even with apparatus this complex, we can still predict how it's going to behave. Well, not me personally, I don't understand these things, but computer experts understand what's going on there. For them, it's all predictable. In which case, what if someone were to examine the workings of my brain in the same way as a computer engineer can examine the workings of the computer? He examines my brain just before I make my decision as to which sweet to take. He applies the laws of nature and predicts with certainty what the state of my brain will be after making this decision, this so-called decision. Surely that way he will know what my choice is going to be, that I'm about to pick the blue one, even before I know what I'm going to do. It's all predetermined. I have no choice, no real choice. I'm just going through the motions. This is the so-called free will determinism problem. How to reconcile the grinding predictability of the physical brain and the physical world in general with the mental sense that the future is open, the sense that it's up to us to decide what it will be. We have freedom to make genuine choices. It's a problem that scientists and philosophers have wrestled with for centuries. Recently, some have sought to solve the problem by calling upon quantum theory. Quantum theory is necessary for the description of the behavior of very small objects, atoms and subatomic particles. What it shows is that on the very small scale, the future is not predictable, not with absolute certainty. The electrons that make up an atom, we never know where we're going to find them next time we look. And no, it's not a case of look more carefully or invest in more expensive measuring equipment. No, this is a built-in uncertainty, an uncertainty sort of that's absolutely fundamental to nature itself. At the subatomic level, all we can ever hope to do is to predict the odds of various possible outcomes, which of course doesn't seem to square with normal everyday life where things are predictable up to a point. But here we're not looking at individual atoms. This array is made up of a vast number of atoms. So what we're looking at here is the average behavior of many atoms. And that average behavior is predictable, but not the behavior of the individual atom or subatomic particle. That is governed by... So, this raises an intriguing possibility. If the action of the brain corresponding to the making of a choice, if that action is something happening on the very small scale up here, perhaps involving the movement of an individual atom, then the behavior is not predetermined. It's subject to chance, random chance. And some have latched onto this to claim that that is how we come to make a free will decision. The blue or the red. What could I do? Okay? Blue tails, red heads. But is that me making a decision? A conscious decision? No. That's me leaving it to chance, opting out of making a conscious decision. No, quantum uncertainty, with its dependence on chance, seems to go the way of all previous attempts to solve the free will determinism problem. It's a problem like that of consciousness itself, a problem we seem to be stuck with. I can't see how it will ever be solved. Not to everyone's satisfaction. What kind of world do we live in? What kind of universe? Well, thanks to telescopes, not like, for example, that one over there, and today especially the Hubble telescope out in space, we know a great deal about what's out there, the structure of the universe, how it came into existence, how it got to be the way it is today. Beginning with planet Earth, we know it to be part of the solar system. Our sun is a star, much like all the other stars. Stars are gathered together into great swirling whirlpools called galaxies. Our galaxy is called the Milky Way galaxy. Galaxies, in their turn, are gathered into clusters of galaxies. And these clusters stretch out into space as far as we can see. And when we observe distant galaxy clusters, we find that they are all receding away from us. The further off a galaxy cluster, the faster it's receding into the distance. And all this seems to point to the idea that at some time in the past, all the matter of the universe was gathered together, the Big Bang, and everything flew apart. The motion of the galaxies we see today is exactly what we would expect if it had resulted from such an explosion. Not only that, but knowing how fast a galaxy cluster is moving and its distance from us, we can work back to when everything must have been together. In other words, when the Big Bang occurred. And it turns out that it happened 13.7 billion years ago. That gets switched off round about here, and then we get the normal sort of expansion we see today happening along here. We call that the expansion. Edwin Hubble was the astronomer who first discovered that the universe was expanding. In saying that inflation took place over a brief period, I mean really, really brief. It all happened in the space of a tiny, tiny fraction of a second. That's right, we're talking about what happened a tiny fraction of a second after the instant of the Big Bang. Yeah, it's a truly mind-blowing achievement. The Big Bang was such a cataclysmic event that we assume it must have marked the point when the universe came into being. In which case, it appears natural to ask, what caused it? What caused the Big Bang? And what came before the Big Bang? But there's a problem. It's all very well talking about what happened immediately after the instant of the Big Bang. Inflation, tiny fraction of a second. There is all the difference in the world between saying what the universe was like a tiny fraction of a second after the instant of the Big Bang and what it was like at the instant of the Big Bang, let alone what might have happened before that instant. You see, at that instant, all the matter of the universe would have been squashed down to a point, a place of no volume. So the density would be infinite. And there's no way our physics can handle a situation like that. We call it a singularity. We can't handle it, but at least we can give it a name. We call it a singularity. And that means we have no hope of extending our investigation through that instant to what might have preceded it, to what might have caused the Big Bang. Okay, that's reason why the question, what caused the Big Bang, can't be answered. But there might be an even stranger reason. They also mark the coming into existence of space and the coming into existence of time, bound up in Einstein's theory of relativity. So, there was no time before the Big Bang. Now, for those seeking a cause of the Big Bang, there's a problem here. I stir the coffee, that's the cause, and what you see happening there is the effect. First the cause, then the effect. The effect here is the Big Bang. So the cause of it must have existed before the Big Bang. But where the Big Bang is concerned, there is no before. Extrapolate through that point of infinite density. No, the problem goes deeper than that. The question probably has no meaning. There is no time to accommodate a cause, so there can't be a cause. St. Augustine was once asked, what was God doing before he made heaven and earth? And Augustine replied, he was creating hell for people who ask questions like that. In fact, this is a fairly common problem when exploring science at its deepest levels. It's the boundaries of the knowable. Perfectly fair question, what caused the Big Bang? But is it? No. A much better question in this particular instance is this. Why is there something rather than nothing? We're not talking specifically about the mechanism of the Big Bang. No, we're asking the very general question, why does anything exist? You see, if nothing existed, or had ever existed, why should anything exist? But as soon as something exists, anything at all, then the questions start. Why does this particular kind of thing exist and not something else? What is responsible for their existence? And once having got something into existence, does it need an agency of some kind to sort of keep it in existence? Science does not address questions like that. It takes the world as a given. Its job is to describe the world as it happens to be a world in the first place. To say that the question, why is there something rather than nothing, can be ignored. It might well be a meaningful question. It simply lies beyond the boundaries of scientific inquiry. The sun and the other stars are great balls of fire. The depths of space, by contrast, are freezing cold. The distances involved are immense. It's perhaps not surprising that many people view the universe as hostile to life. The physicist Steven Weinberg once dismissed life as a more or less farcical outcome of a chain of accidents. But first impressions can be deceptive. Here are some of the laws of nature, the laws that governed how the cosmos evolved and govern all that goes on around us now. It turns out that if these laws had been fixed at random, with the strength of the gravitational force or the strength of the electrical force or the masses of the subatomic particles or the violence of the Big Bang, if any of these had been chosen purely at random, then the chances of having a world with life, any kind of life, would have been virtually zero. So the universe appears to have bent over backwards to accommodate life. This observation goes under the name the anthropic principle. As another physicist, Freeman Dyson, somewhat colourfully put it, the universe knew we were coming. So how are we to account for it? The way the universe is so life-friendly. Was it specifically designed as a home for life by some creator? That's one possibility, but that of course takes us way beyond the realms of science. Some seek to solve the problem by suggesting that our universe might not be alone. There are other universes, lots of them, perhaps an infinite number of them. The whole ensemble is called the multiverse. And the idea is the laws of nature are different in all the individual universes. In the vast majority of them, there is no life because one or other of the conditions was not satisfied. But once in a while there comes along a universe which happens to have the right set of conditions for the development of life. We, being a form of life ourselves, must of course find ourselves in one of these freak universes. Well, fair enough. That would account for why our universe is life-friendly. But that simply raises another problem. How are we ever to prove that there are universes other than our own, and that they are run on different lines? Other universes, by definition, are not part of our universe, and so cannot be contacted. So it could be that the multiverse idea might also lie beyond the realms of science. When thinking about our universe being life-friendly, one can't help wondering whether there might be other forms of life out there. And if there is life, and it's intelligent, how does that affect the status of us humans? Well, as far as our solar system is concerned, the planets circling our sun, there might be some forms of very primitive life. We should have the answer to that quite soon as a result of planned space probes. But not intelligent life. No, if ET exists, it must be on a planet going around some other star, what we call an exoplanet. And there's no shortage of those. Several hundred have been found, and the tally increases weekly. Most of them will not be habitable. But from the law of averages, there must be many, many Earth-like planets out there. Planets where intelligent life could flourish. Which is not to say that it has. So a big question is whether or not there is extraterrestrial intelligent life. And if so, what's it like? Evolution on Earth took a very long time. Billions of years. So on some other planet, it has only to get out of step with what happened here on Earth to only a small degree for ET to have reached our level of intelligence, the intelligence of a Charles Darwin, to have reached that level a long, long time ago. So that means they must by now be way ahead of us. Except the human race has got this far in intelligence because in the past there was survival value in having a superior intelligence. You had a better chance of surviving to the point where you could mate and pass on your superior genes. But does that still apply today? Do the more intelligent people today have more children than the less intelligent? If anything, I'd have thought it was the other way around. After all, the more intelligent you are, the better your chances of getting a well-paid job. And the better paid job leads to a higher standard of living. And the fewer children you're likely to have. If that's true of us, perhaps it's also true of ET. On the other hand, when ET reached our stage of development, he would know all about DNA and genetic engineering. For all we know, they might be heavily into genetically engineering designer babies with superior intelligence, a case of directed evolution rather than relying on evolution by natural selection. In which case, as we previously thought, they will now be vastly superior to us. On the other hand, when they reach our stage, they discover nuclear power. And in all probability, in a comparatively short, perhaps that's the fate of all intelligent species throughout the cosmos. They reach no further improvement. Go and visit them. Science fiction adventure stories. No. Hardly. The distances are just simply too far. Space travel is not the answer. The other approach is to search the skies for any signals indicating that ET is trying to communicate with us. Such searches have been carried out for many years by the SETI program, the Search for Extraterrestrial Intelligence, but so far without success. They'll find anything. Even if ET exists, they might not have the means to communicate with us or the desire to communicate with us. The situation is, it's not under our control. It's up to ET. Perhaps we're destined never to find out about intelligent life elsewhere in the universe. I'm not just thinking of outer space, I mean any sort of space. The space here, the space where you're sitting. Well, the answer seems obvious, you know. Empty space is just another name for nothing. But that's not how the modern physicist views it. Take, for example, a space station. It's orbiting the Earth. Why? Why doesn't it just go drifting off into outer space in a straight line? Gravity. The Earth's gravitational force acting on it. Oh, fair enough. But what if an astronaut steps outside the spacecraft? He too is orbiting the Earth, and in more or less the same orbit. Why? Earth's gravity again. But the astronaut is much lighter than the space station, so in order to get him to go in the same orbit, the gravity force on him has to be less than on the craft. So how does gravity know how much less it has to pull on him than on the craft? And in any case, why would gravity want them to go in the same orbit? The puzzle is solved once one sets aside the idea of the Earth exerting a gravitational force and instead thinks of gravity curving the space around it. Okay, well, this is something I've rigged up. This surface represents normal empty space. And if we have an object going through that space, perhaps a spacecraft, then the natural path to follow is a straight line, like that. But look what happens once I put a heavy object into that space, the Earth. Now you see what it's done to the surface. It's curved the surface. So now the natural path for an object passing through it, like a spacecraft, is no longer a straight line. It's a curved path, a bit like this. Okay, well, forget about the spiraling in. That's just due to the friction we've got here. But for the spacecraft above the atmosphere, there's no friction to speak of, so we get a steady, repeated orbit. Let me just show you how it comes about that the astronaut and at the same sort of speed. As you see, I've happened to have got a curved surface here, and now we'll make the heavy ball represent the spacecraft, and the lighter ball is the astronaut who's just stepped outside the spacecraft to go for a spacewalk. So the reason why the astronaut and the spacecraft follow the same orbit is that that is the natural path to follow. The natural path is no longer a straight line, a straight line which has then got to be curved because of the action of a force. This way of viewing gravity we owe to Einstein. It's part of his theory of relativity. So space is not nothing, space is something, a mysterious something that can be curved. And that's not all. The universe is expanding. Distant galaxy clusters are receding into the distance. This is all in the aftermath of the Big Bang. But that's not to say the galaxies are moving through space into an outer space where previously there had been nothing. No, they're moving because it's space itself that is expanding. The space between us and the distant galaxy is carrying the galaxy along on a tide of expanding space. Okay, here I've got some galaxies. Because the rubber in between the galaxies has expanded and carried them along with it. Okay, that's what's happening out there. Space, so-called empty space, is pushing the galaxy clusters apart. Of the various stages of the expansion of the universe. The Big Bang occurred here, and that's followed by the more gentle, normal kind of expansion, like what I showed you with the balloon, because of the mutual gravity between the galaxies. But look what's happening here. The rate of expansion is now increasing. This is due to what is called dark energy. Space, empty space, has energy. And whereas matter attracts through its gravity, empty space, through its dark energy, repels. But it can also push around heavy things such as galaxies. It's not simple at all. It's a deeply mysterious something. But what? We all start off thinking there's just the one time, the same for everyone. But Einstein's theory of relativity shows that this is not the case. Two people moving relative to each other, they have their own times and they're not the same. At normal speeds, me moving relative to you like this, at these sorts of speed, the difference between your time and mine, it's not obvious. It's too tiny to notice. But at high speeds, really high speeds, the effects become enormous. Suppose, for example, we have a spacecraft and it's flying to a distant planet. And just suppose it's going at a speed equivalent to, well, let's say 9/10 the speed of light, around 270,000 kilometers per second. Not realistic, but just suppose. It's time itself that is slowed down. It's called time dilation. Now you might think that the astronaut would find this all very strange, living in a world of slow motion. But no. His thinking processes will be slowed down in the same ratio. And if you look at a slow watch with a slow brain, it appears normal. So for the astronaut, everything happening in the craft appears perfectly normal. It only appears slowed down to the mission controllers. But you might think, well, surely the astronaut will know his time has been going slow when he arrives at the distant planet, the expected time. No. There's a second effect of relativity theory. This is the situation as seen by the mission controller. Here we have the Earth, and this is the planet to which the astronaut is journeying. But according to the astronaut, this is what it's like. Relative speed affects not only time, but also distances. According to the astronaut, travelling at 270,000 kilometers per second, the distance from the Earth to the planet is only half of what the mission controller says it is. It's squashed up. The Earth and the planet themselves, they're squashed up. In fact, any length seen to be moving relative to the spacecraft, according to the astronaut, will be squashed up. It's what we call length contraction. So we have time dilation and also length contraction. The mission controller says, your time is running slow. The astronaut says, there's nothing wrong with my time. It's your distances that are squashed up. It all makes perfect sense. Except it doesn't agree with what the mission controller says is going on. Okay, if this is the first time you've come across this sort of thing, then it all seems quite bizarre. It's all been tested out and found to be true. Not with spacecrafts and flying about at speeds close to that of light, but here. High energy physics laboratories like CERN, just outside Geneva. Here we can check out Einstein's theory using subatomic particles hurtling around the particle accelerator at speeds that are indeed very close to that of light. This is the Large Hadron Collider. If you yourself were to travel at the speeds achieved here, you'd live to be 500,000 years old. That's time dilation. As I say, all this sounds very confusing. You know, different people having different ideas about lengths and times. But fortunately, there is something the astronaut and the controllers over there, in fact, all observers can agree on. It comes about like this. We're used to thinking in terms of three-dimensional space. Up, down, sideways, backwards, forwards. So, three axes at right angles, like this. A separate one-dimensional time. Three-dimensional space as it moves up the time axis. But what if we're wrong and they are joined together? A four-dimensional space-time. That's what we call it, space-time. What would we expect to find in this four-dimensional space-time? Well, to be characterized by a particular point in space as measured along the three spatial axes, a particular point in time as measured along the time axis. In short, we're talking about events. One event might be the launch of the spacecraft at that's its point in space. The launch also taking place at a particular point in time. 3, 2, 1, blast off. A second event will be the arrival of the spacecraft at the distant planet at a later point in time. Now what one finds is that although the two sets of observers, the astronaut and the mission controllers, they don't agree about either the spatial distance, about the interval between those launch and arrival events in four-dimensional space-time. And it's because everyone agrees about what the situation is in four-dimensional space-time. Our familiar time and space, they're nothing more than appearances. Appearances of this reality. Subjective appearances as seen from some specific point of view. Okay, now, you know, different appearances. Well, And take this pen. It has many different appearances depending on the angle one is looking at it. Now, sometimes it appears short, but sometimes from another angle, from another point of view, it appears long. This is because all we see with our eyes or photograph with a camera is a flat two-dimensional projection, a projection of something that is actually solid, something that exists in three spatial dimensions, not just two. So what we're saying now is that space by itself is but a three-dimensional projection, a projection of something that is actually four-dimensional. And the time interval is nothing more than a one-dimensional projection of this four-dimensional reality. As Einstein once said, henceforth we deal in a four-dimensional reality, not a three-dimensional reality evolving in time. Times and distances. But does it? This four-dimensional space-time is sometimes called the block universe, and also all of time, present and future. This point here, that represents the present instant. And then on this side, that point there is when we started the program, and I say, the subject of time has always fascinated people. And here on the other side, that's when I say, fathom the riddle of time. And the program comes to an end. And you can take a headache pill on an equal footing. According to the block universe idea, the future already exists. It's out there, waiting for us to come across it and experience it consciously. It's static. Nothing changes in the block universe. Changes occur in time, all right? But time isn't out here. Time is in it. But if nothing changes, how can we experience a flow of time? Time rolling on. How can we have this impression that whatever exists is what is present instant? We can't be sure because it doesn't yet exist. What we're talking about now is the mental experience of time, an experience that seems not to be reflected in the physics. In fact, the physics community is deeply divided over the concept of the block universe. That space-time is real, that it's the reality, instead of some abstract mathematical thing. So, does all of time exist, including the future, in some sense? And if so, in what sense exactly? Will we ever fathom the riddle of time? Or is this another encounter with the boundaries of the knowable? What is everything ultimately made of? It was once thought that the answer was atoms. Atoms, the fundamental building blocks of matter, which cannot be cut, which is hardly the case. Atoms have an inner structure. They consist of a central nucleus surrounded by tiny particles called electrons. The nucleus has a positive electric charge, the electrons a negative charge. And it's the electrical attraction between these charges that holds the electrons close to the nucleus. Electrons are considered to be truly fundamental. They really are one of the basic building blocks of the matter we see around us. The nucleus, is that fundamental? No. It too has an inner structure. It's made up of neutrons and protons. The neutron and proton are very similar to each other. It's just that the proton carries a positive electric charge, whereas the neutron has none. It's the charge on the protons that gives the nucleus as a whole its positive charge. But you might be thinking, hold on, But won't the nucleus? No. Things are more subtle than that. Okay. Here I have two protons, right? I'm going to push them apart. That represents the electrical repulsion. But they don't separate. Why? Because there's another force at work, an attractive force. Nuclear force is more powerful than the repulsive electrical force. And that's what leads to an overall attraction holding the nucleus together. And a neutron fundamental, like the electron? Nope. When you look inside them, you find that they're made up of tiny, tiny particles called quarks. A bit like the pips in the apple. Two types of quark, what we call the up quark and the down quark, which we denote by U and D. The proton has two ups and a down, and the neutron two downs and an up. So both the proton and the neutron are made up of three quarks each. Quarks, like electrons, are believed to be truly fundamental. They mark the end of the line. So everything is made up of two kinds of quark, up and the down, together with the electron. And to this we need to add a fourth particle, the neutrino. Neutrinos are produced, for example, in the nuclear reactions going on in the sun. The neutrino is like the electron, except that it carries no electric charge, and so it doesn't experience the electrical force. And like the electron, it doesn't experience the strong nuclear force either. That's only felt by the quarks. But it does experience what we call the weak nuclear force. That's a force responsible for certain kinds of radioactivity. So because they experience only this weak force, neutrinos are famous for hardly interacting with anything at all. 100 billion solar neutrinos can pass through my thumbnail every second, and I don't feel a thing. So there we have it. Constituents of matter, the up and the down quark, the electron and its neutrino. What could be simpler? Except that it is not that simple. It's much more interesting. It accelerates protons round in a huge circle. Two beams in that tube, travelling in opposite directions, one going clockwise and the other anti-clockwise, and at various points they're made to collide. Why? What's it all about? No, the original motivations, but actually something much more intriguing than that happens. New matter being created. But didn't we learn at school that matter can be neither created nor destroyed? Yes, and that's still true. No, this new matter arises from the brought into the collision by the original bombarding particles. It's a consequence of Einstein's famous equation E equals mc squared. Is that some of these new particles carry properties that ordinary matter doesn't have. Properties that have been given quirky names. Strangeness, charm, top and bottom. I myself had the privilege of belonging to the international collaboration that was the first to make a direct sighting of a particle carrying charm. Now, like the proton and the neutron, these new particles are made up of strongly interacting quarks. But because of these new properties, the new particles can't all be made of just the two types of quark that we've been talking about so far, the ones that make up the proton and the neutron. No, we need to add more fundamental particles, different quarks, one carrying charm, one carrying strangeness, one for top and one for bottom. Three groupings of four particles, each of these groupings called a generation. Three generations, 1, 2, and 3. These are the ultimate constituents of all the matter we see around us, plus all the more exotic types we create in these high-energy collisions. Unraveling all this has been a wonderful achievement. But we're still left with some worrying puzzles. 3 generations. Why 3? Why not just 1? Or if you're going to have more than 1, why not an infinite number? What's special about 3 of these particles? What determines the values of their masses? And their masses are very odd. The tau particle, for example, then the electron. As for the neutrinos, they are so incredibly light that for a long time it was thought they had no mass at all. Weighs 50 to 100,000 times as much as the up quark. What does it all mean? We simply don't know. In fact, in order to make sense of our understanding of the nature of matter and the forces between them, we need to feed in by hand the values of 19 different parameters. Being a high-energy physicist myself, it remains my hope that one day, someday, we shall be able to find answers to these outstanding questions. But I can't help wondering how close we might be getting to the boundaries of the knowable. Well, what is light? For a long time it was thought the answer is obvious. Light is made up of waves, electromagnetic waves, undulating electric and magnetic forces travelling through space, much like waves on the surface of a liquid. Okay. This seemed obvious for a number of reasons. For example, when waves pass through a narrow gap in a barrier, they spread out somewhat to the side rather than going straight on. And that's what light does. Put 2 gaps close together and the humps and troughs from the 2 gaps overlap and interfere with each other. This gives rise to directions where the humps and troughs are in step and they reinforce each other. And then in between, the humps and troughs are out of step, they cancel each other out, and you get very little activity. Now, this is exactly the kind of behavior we get with light. Pass light through 2 parallel slits, and we get bright beams going off in a number of directions with little in between. Liquid you get from a spray can, for example. Okay, I can demonstrate this like this, that light is made up of waves. Except, if you examine closely how light gives up its energy when it hits the screen, using a very weak beam, all you see at first are the smoothed out distribution you might expect if light were a gently undulating wave. As more and more light arrives on the screen, so you get more dots and the interference pattern begins to emerge. But note, the energy is being given up as localized dots. We call these tiny bundles of energy photons. Can only be explained by saying light is particles. So the crucial question becomes, how can something be both a wave, spread out over space with a succession of humps and troughs, point like particles? This dilemma is known as the wave-particle paradox. And atoms are made up of a nucleus surrounded by electrons. The nucleus is made up of neutrons and take a beam of electrons like the ones you get in the older style TVs and computer monitors. The electrons are emitted from an electron gun at the back of the tube, and then they travel to the screen where the energy that gets converted into the light that makes up the picture that we see. They hit the screen like a hail of tiny bullets. And this shows how those interference electrons, the other constituents of matter, protons, they also exhibit wave-particle duality. Complete molecules, everything is afflicted by wave-particle duality. So, well, back in the 1920s, the Danish, so for example, take the case of the electron in the TV, and hence where exactly to find it on the tiny particles, how it interacts when it gets to its destination. There's never any call to have to use the concepts wave and particle at the same time. This is solved. But the solution comes at a price. The price is such questions are meaningless. Suppose, for example, out there in empty space there's an electron on its own, not being observed, not interacting with anything. Under those circumstances, what is it? Is it a wave or is it a particle? Observations. It's a misuse of language to try and use those same words to describe what might exist in between the observations. What you eventually write down in your science textbook is a description of. It is possible to ask whether there is still concealed behind the statistical universe of perception a true universe in which the law of causality would be valid. But such speculation seems to us to be without value and meaningless, for physics must confine itself to the description of the relationship between perceptions. The relationship between perceptions, the relationship between observations. One of the most fascinating fields of study at the present time is the theory that the fundamental constituents of nature are not point-like particles, but strings. Tiny vibrating strings called superstrings. A bit like this. And depending on how the string vibrates, you get different particles. So this might be an electron. That might be a quark. And this might be a bundle of light energy called a photon. Each different particle is a different mode of vibration of the same sort of string. Now with a string, only certain modes of vibration are allowed. Only certain modes of vibration are allowed. And these different modes will have different energies. And because energy and mass are related, Einstein's theory of relativity, E equals mc squared, E the energy equals m the mass. Because of that, these different allowed energies will correspond to different allowed masses. In other words, only certain masses are allowed, which is exactly what it is with quarks and electrons. Now, the fundamental particles differ in mass, but they also differ in other ways. Some have electric charge, others don't. Account for the additional properties by invoking yet further in the way the superstring vibrates. Vibrate in two directions, that way and that way. The ends not being fixed, and that will give you vibrations in that way, which will add variety. Well, a bit like this. Okay. With a slinky spring, you can... well, it turns out that if we could have vibrations of this, which would be great. Take that pointer over there. The other day I noticed there was a chalk mark on it. I meant to clean it off. How can I specify where the mark is on the pointer? Well, how far was it from the end? Well, I noticed it was 18 inches. Well, let's go and take a look. 9, 18, no mark. But wait, in saying it was 18 inches from the end, we haven't specified precisely where the mark is. All that tells us is that it's somewhere around the circumference of the cross-section that's 18 inches from the end. If I twist it round, there we are. Here are the three familiar extended dimensions. We have x1, x2 and x3. And what I've tried to do here for that point there is to show you two extra curled up dimensions. We've got x4 there and we've got x5 there. And that's as far as I can go as far as the drawing is concerned. And we can't in fact form a mental image of it. In fact, there should be 6 curled up dimensions there. And not just true of that particular point in space, but of every other point in the normal conventional 3-dimensional space. 6 extra curled up dimensions at every point, as well as the 3 extended ones, being superstrings vibrating in 9 spatial dimensions and 1 dimension of time. But the worrying thing is that despite so many people working on this problem for the past 30, 40 years, they have yet to come up with a single prediction that could be verified. You see, it's all very well talking about string theory, but there are many variants of string theory. You know, the geometry of the curled up dimensions might be more like this. x4 and x5. Or some other twisted topology. Not 9. Same goes for the superstrings themselves. They are tiny. Forget about the Large Hadron Collider at CERN, 27 kilometers in circumference. That's absolutely no good at all for seeing strings. The strings are believed to be so small, it would take an accelerator the size of a galaxy in order to be able to observe them directly and to check that they really are strings, finite-sized strings, and not point-like. So what does that mean? Are we destined never to know whether this attractive idea is true or not? These are but 2 of the major questions facing fundamental science today. What we've been looking at in this series is not meant to be an exhaustive list of outstanding questions facing science today. Other scientists would doubtless have liked to see mention of, but when we have discovered whatever is open to us to understand, when we have finally come up against the boundary of the knowable in all directions, when will that be? Who knows? 100 years from now? 1,000 years? Indeed, I don't see how we, or more strictly speaking, our descendants, how they will even know when science has come to an end, rather than thinking that it's just going through a particularly boring bad patch, which is itself quite a thought. Not only are there things we shall never understand, we shall never even be sure what it is we shall never understand.